science like there's no tomorrow.
Hello, welcome everyone after the break. Today is block number 2 of the lecture number 11 of the financial engineering course. Today we will concentrate on the labor market model. In particular, we'll be discussing the extensions of log normal market model with stochastic volatility. And the second part of today's lecture will be concentrated on convexity corrections, convexity adjustments. Let's take a look. So in the previous lecture, we discussed the log normal assumptions in log normal labor market model on either terminal or the spot measure. Today, we will extend the labor market model with stochastic volatility. I will show you that if you simply assume log normal, if you take a labor market model and you simply impose instant dynamics for the labor process, you will encounter extremely difficult process for the variance. So simple and naive way of handling stochastic volatility under the labor market model may lead you to some very complicated system of SDs that you may not be able even to solve efficiently. So the approach we will stick with is the, let's say, the naive approach of taking the Heston model, and I will show you what the problems are associated with. Later, we will fix the associated problems, in particular the problems between the correlations between LIBORs and stochastic volatility, variance, and the relation of the impact of the correlation on implied volatility smiles and skews. So the problem with standard stochastic volatility model of Heston and measure changes is that if we change measure in the LIBOR market model, the measure transformation will also imply some correction term, a drift change in the variance process. Therefore, it is very beneficial to have zero correlation between variances and LIBORs. Of course, the cost of such a zero correlation assumption is that the model will not be able to generate enough skew, because skew in the Heston model is implied from the correlation. For that reason, we will extend the framework. I will introduce so-called displaced diffusion parameter or displaced diffusion of the volatility, such that we will be able to impose skew, but not via the correlation, but via the displacement of the volatility. Next part, I'll be talking about the so-called freezing technique. So this is a technique which is often used when talking about approximating of the LIBOR market model. It is very much straightforward, and I see that often people use this approach. I will show you what are the problems with this technique and also what are the traps and pitfalls associated with freezing and what kind of problems you may encounter if you have a complicated and, let's say, sophisticated model like LIBOR market model, that by freezing, essentially you may destroy all the nice features of the model that we have started with. So freezing, you have to be very careful how to apply it and don't abuse it. This is very important. The last part of the lecture will concentrate on convexity corrections. I will show you what are the convexity problems, when we can encounter problem of convexity adjustment, and how to handle it. Also, I will discuss here kind of possibility of inclusion of implied volatility smile and skew in the convexity adjustment calculations. Here I'll also refer to the so-called Braden-Litzenberger approach, where we can include implied volatility smile and skew in the adjustments for the volatility, for the convexity corrections. I will finish this lecture with a summary and homework. Today we will have 3 assignments that will give you more depth, more insight into LIBOR market model and also convexity adjustments. So I hope you enjoy it and have a good lecture. Now let's define the Heston type of model for LIBOR rates and see what are the consequences of this particular dynamics choices and what are the problems if we just directly apply the dynamics of Heston for LIBOR rates. What are the problems, what kind of surprises we may expect. So this is a definition of the Heston model if we just directly apply to LIBOR LMM. So you see everything nicely fits because LIBOR, it is still the martingale under the T forward measure. So this is TI forward measure. So we see there is no drift. We have this sigma I, which is constant. We have a stochastic volatility. Here is the dynamics for the volatility. So it's a CIR. So this is just application of the Heston model to the LIBOR market model. And here Okay, small differences here because we have the sigma I, which is constantly multiplied, but of course we can include the sigma I in the square root process. So that's not a real problem as long as we scale it with a constant. The dynamics of the process basically is the same. So let's see what comes out if we just apply this. This will be our starting point, and we apply the measured changes we have already discussed. So you see here we also assume that we have all the correlations between LIBORs. So this is important that LIBORs are correlated. So that's a key element. We cannot assume this to be 0. And then we also assume that LIBOR I is correlated with the variance. So we have this Brownian motions that are correlated. So this is also very important because, as you remember from the course of computational finance, the whole idea of the correlation in a Hesston model between two Brownian motions is that with the correlation we can impose skew into the model. So as you remember, in the Hesston model, stochastic volatility, which is uncorrelated, generates smile, implied volatility, smile. If we have correlation, basically we may modify this smile into kind of skew pattern. So this is the transition. So the correlation between these two Brownian motions, especially the negative correlation, will impose implied volatility skew. If we assume zero correlation, basically the model has only smile. We have, of course, some parameters, additional parameters, but the correlation is a key parameter in the Hesston model. So okay, so this will be our, let's say, full-blown model with correlations between LIBOR rates. Also, we have correlation between LIBOR and variance. What we do next? First, let's redefine this model and express this dynamics of the LIBOR under the TI forward measure in terms of independent Brownian motions. That would be very handy because we want to perform measured changes. So of course, it's nice to have independent Brownian motions rather than correlated, because this measured transformation uses Grzelak to be much more involved. Then we have to deal actually with matrices and arrays. Actually, in the book, I have shown you some examples how the measured transformations look like if you deal with matrices, like related Brownian motions. It's a little slightly more involved, and I will refer to the book. But here, standard approach is to redefine your model in terms of independent Brownian motions. And of course, here the Cholesky will be applied. So then we have the volatility here for the LIBOR is just independent. It's a first process. And for the variance, we have two processes. One, of course, is this process, this Brownian motion from this process. And then we have this independent second stochastic driver for the variance. Okay, we are interested in changing measure. So we change measure from TI to measure TI minus 1. So we have T forward measure. We are changing to TI minus 1. And from previous lecture, actually previous block, we know this measure transformation. So we are not going to repeat that. And of course, here we have this sigma bar. We know that in our case, in Hesston case, this is the expression here. Yeah? So because we have stochastic volatility, so the sigma bar is slightly more involved because we have additional volatility driver. Okay, and of course, because we have this measure transformation, what we have done here, it will not impact the change for the Brownian motion for the variance process. So this is written here. Because we have those processes to be independent, this transformation for Brownian motion for a volatility process is not affected by this transformation. So far so good. Everything looks very nice. So let's see how this dynamics will look like after we substitute. If we use this definition, because we have to now plug it in here and see, and also we have to do it here, because this is our change of measure. Because of course, this Brownian motion is independent of this one, and this will not change after if we are changing to TI minus 1 measure. However, if we switch this measure, it would also need to be adjusted, and this is the measure transformation. So if we substitute here this term, then let's see the dynamics, how it look like. So for the LIBOR dynamics, we see it's not a big issue because this is exactly what we have seen already before in the log normal or in general LIBOR market case. We have this additional drift term that has to be included. Of course, this drift term will involve also the stochastic volatility. But what happened for the variance process, this is actually the quite interesting part, because you see that our after substitution of the Brownian motion in our dynamics for the variance, so we are here, you see that our dynamics of the variance now also involves LIBOR dynamics. You see, this is the key points here. So okay, we have those Brownian motions here, but this is the problematic part. So if we have Heston model and we start changing measures, assuming full matrix of correlations, then the problem is that our variance process becomes highly complicated, because you see, we cannot anymore use our tools like, for example, exact simulation for the CIR model or exact simulation for the Heston we already discussed in the previous course. This time, the drift for the volatility, it is highly complicated because it involves LIBORs also. So that's not really desired. And also the techniques, handling of a zero bound in the case of CIR, if the failure condition is not satisfied, it's a big issue. Okay, somebody could say, let's impose this correlation here to be zero between LIBOR, ith LIBOR, and the variance. Of course, this will remove the problem because then we end up, this part will be then gone. So the whole this term will be gone. And we end up with a standard dynamics for the variance, for the Heston model. But of course, what about skew? Because the skew in the Heston model is controlled by the correlation. So if you remove this correlation, we would only have smile. So that's a problematic issue, and that's basically means that we cannot directly use the Heston model and benefit from what we have developed already. And we have also discussed in the previous course on handling of the Heston model, simulating, and also fast Fourier transformation. That will be problematic issue. And this is here I represent a little bit of a reformulation when we see that the drift for our variance process, now it is highly complicated. So this is exclamation mark. This is what you don't want to have, because we would also need to develop a technique for those volatilities and how to handle those square roots if those LIBORs, for example, are negative. So this is really a big issue for this model. And this will be discussed in a later block. I will show you how to solve this problem using different dynamics than the Heston model. So Heston model is not good choice for modeling of stochastic volatility in the LIBOR market model. So there are better choices than that. Here, let's summarize what we have seen so far about regarding the Heston model. And this will give us motivation on using different type of dynamics for the process for the stochastic volatility in the LIBOR market model. So the derivation that we have just done shows that the measure change is applied to the Heston model will affect the drift term of the variance process. So we have drift term for the LIBOR that will be affected, but also for the variance process. So this is the big if we talk about Heston and application to LIBOR market model. The LIBOR rates and stochastic volatility processes are correlated, which has a significant impact on the dynamics of the process under measure change. So this consequence, the problem that we have observed, it comes from the correlation between LIBORs and volatilities. And of course, that was the motivation, because we want to have that correlation, because we would like to also model skew, not only implied volatility, smile. Of course, there are some techniques like, for example, parameter freezing techniques that will still facilitate the dynamics for the variance. And freezing technique I will discuss later in this lecture. However, if we start introducing some kind of approximations already at this level, then the whole idea of using this for machinery LIBOR market model, this is not anymore our model we started with. So we start with idealized model that would solve all the problems. And if at this point we introduce some kind of approximations, then I really doubt whether the the strength of the model is preserved. And here's another thing, that the correlation parameter between LIBOR rate and volatility is set to 0. So if we have this zero correlation, then everything is nicely solved. But the problem is that the model may not be realistic. It may not be sufficiently well calibrated to the implied volatility model in the implied volatility data available in the market. So this is something to keep in mind. We need to have a model that would allow both implied volatility smile and skew, because only in that way we can calibrate to the market quotes. And this is the motivation of not using the Heston model for the LIBOR market model, but to use so-called displaced diffusion, and that will be discussed in a minute or two. We have just discussed that the application of the Hessel model for LIBOR market model, it is not really suitable because of the difficulty that we may encounter, especially if you would like to preserve smile and skew. The difficulty we encounter, the dynamics of the volatility process, of the variance process after measure changes. So let's take a look on another candidate, the second candidate of today's lecture. Actually, you will see this one is much more successful in reaching, satisfying the conditions of health, is the so-called displaced diffusion, stochastic volatility. So this is displaced diffusion is actually the first part. And then, of course, we have a volatility part, which is stochastic. So it's a stochastic volatility, displaced diffusion. So how this displaced diffusion looks like? Already in this lecture, we discussed about shifted log normal processes. And you can see, actually, this is very much alive. So what happens here? Sigma I is a constant function. We have this stochastic volatility, so we forget about this. And this part here, this is, see this function beta, it tells us how we are interpolating essentially the LIBOR between its initial value. You see, this is L T0, and also the value of the LIBOR, which is our process. So we see that this part here, it kind of displaces our LIBOR process between initial value and the process itself. So you see, this is actually the trick. This is the so-called displaced diffusion, because you see, we are actually looking at diffusion because it's next to the volatility. So this is playing with the volatility function. If we have, for example, a log normal process, and we introduce this kind of displacement, the log normal could be also negative. Yeah? So this is the equivalent of the same idea as we had by shifting of the process. You see, this is the same here. So this part is constant. We could say we are adding extra value, extra some coefficients, or we are moving the distribution by this kind of factor. And of course, here we are relating this movement, or let's say displacement, with respect to the initial value. So depending where the initial is, this is how this move will look like. And of course, this is, you can see this beta is between 0 and 1. So in the case of 0, then this part will be gone. Then we have only the constant part here. This means we are dealing with a Bachelier type of dynamics. Of course, assuming that volatility is constant. So it's a normal distributed because there is no stochasticity here anymore. And in the case we choose beta equal to 1, then this part will be 0, and then we're having log normal. So displaced diffusion, you can think of interpolation between normal and log normal processes. This is kind of a relation between the two. And if beta is larger, then becomes more log normal, and if beta is smaller, becomes more normal. So this is the idea. And of course, we have also the stochastic volatility part. That stochastic volatility part is responsible, in this case, for smile. So you see here, we have very important assumption in this model, because we assume that there's a zero correlation between these two Brownian motions. So LIBOR dynamics is not correlated to the Brownian motion of the variance process. And this was something that we really needed in the measure change technique. So as you remember, measure change was really critical because it introduced additional terms in variance process. By setting the zero correlation, that solves the problem. And how we fix the, let's say, because if we indeed impose zero correlation, that will impact the smile and skew, and that is compensated with this displacement. So displacing approach, by introduction of this beta, we essentially are implying or introducing to the model skew in the dynamics. So displacement means skew, and then that skew would compensate for this skew which is gone because we assumed zero correlation. So you see, this is some kind of offsetting effect. Because we want to have skew, we can simply assume zero correlation. However, if we introduce zero correlation, because we want that for the measure change, we have to compensate that effect by introduction of displacement into volatility. For the rest, the variance process stays the same. Of course, now we already know that this process will not have any problems anymore with measure changes, because the variance will become kind of independent of all the LIBORs. So we have one variance process, and we have an N or M processes for LIBORs. So you see, now we have one variance for all the processes, and then we have also those scaling parameters that will correspond how much LIBORs are related to the how much, let's say, portion of the stochastic volatility they obtain, and that is controlled by this beta and sigma I. So this is nice. And of course, now the second point would be, because we know that this is displaced diffusion, we haven't so far worked on how this process can be linked to the processes we have discussed previously in this course. In the next few slides, I will show you how to relate this dynamics, this displaced diffusion dynamics with zero correlation, to the representation of the Heston model. So you will see that actually this model is a special case of the Heston model. So this is something also very nice to have, because we can use the benefits of the Heston model, like for example Fourier transformation, in order to calibrate model to couplets. This will be in our case very important. What is also important is that from the perspective of calibration, is that each LIBOR, you remember we decided that we are going to work on the spot measure, which is beneficial. However, if we talk about calibration, then each of the LIBORs you would calibrate under its own measure. So we don't need to, if we calibrate LIBOR, this Li, we don't need to change measure to the spot measure. We can just calibrate under its own measure. Then we benefit from the fact that there is no additional drift corrections. And then if you like to evaluate some derivative, then we can change measures. So the parameters will not change if you calibrate it to your model. Parameters will not change if you change the measure. So this is a very important takeaway. So you don't need to start with the spot measure. You can start with convenient measure like here that we want to, that we can calibrate to couplets using Fourier transformation, for example. And then if we want to price exotic, then we change measure. And then we don't need to care about those parameters, because those parameters are already pre-calibrated, they're fixed, and measure change will not impact the volatilities. So this is the calibration of this process is only about calibration of volatilities. So this is very important. Of course, we still have to deal with the correlations between LIBORs, but that it's not covered in this course. This could be handled by some kind of parameterizations that I already have mentioned. Okay, let's take a look at the displaced diffusion, what it is. So here in this figure here, I removed, just for illustration purposes, I didn't consider the case of the variant. So I have implemented only the displaced diffusion, only this part here. And I forgot, not forgot, but I decided not to show you the impact of the variance, just to focus on the part of the skew. This is why, for example, if we see beta equal to 1, that's essentially equal to the log normal case. There is no smile, just flat line. Then basically the model collapses to Black-Scholes model. And not for Black-Scholes model, they only have implied volatility smile. Once beta is becoming here half, for example, this is the yellow line, we introduce some skew. And then once beta becomes decreasing, even I introduced here negative value beta, you see the skew becomes more and more pronounced. So further you go away from 1, decreasing sense, then there is a more skew in the model. And here I show you the impact of sigma, so impact on a second parameter of this model on the implied volatility shape. So you see sigma represents the level, beta represents the skew. And then we have, if we go back, and if we would introduce this process for the variance, this would introduce us also additional smile effect. So there would be nice combination between smile and skew. Of course, there will be also this mean reversion volatility here, curvature. So that would be like giving us enough flexibility to calibrate the model to market instruments. The discussion regarding the parameters, their impacts on implied volatilities, I recommend to go back to the computational finance course, where I spent quite some time to discussing the impact of all the parameters in this dynamics. Right now, I'm also not going to discuss the Python implementation because it's very much straightforward. It is available, however, for you, so please download it and you can play with this these simulations. It's very straightforward, actually, this simulation. This is why I don't want to dedicate more time to it. The remaining part of this block, I would like to concentrate on linking displaced diffusion with stochastic volatility to Heston model. To Heston model, because then you can actually use the techniques we have discussed in the previous course regarding fast Fourier transformation to price your model to couplets, for example. So if we just look at the dynamics of the LIBOR, we can slightly reformulate it. So if we take this beta, you see in this process here, if we take beta outside of this bracket, then this is equivalent with this term. So here we have 1 minus beta, and then we multiply this fraction here. And of course, this part we can take also, we can divide both sides of this equation. Then this is equivalent with this. And here we end up nicely with beta sigma I. And then this, let's say, displacement part, it's in the denominator on the left-hand side. We also noticed that the dynamics, so the dl plus some constant a, it is unchanged. So this is basically because this is constant, the dynamics will not change if we shift it with some constant a. However, the initial would change. So if this will be new process, we have to make sure that the initial will be still affected by this a. However, the dynamics will not be affected. So if we follow this strategy, we can, this part is constant, so we can always add to this L here. So this is what we do here. So then we have on the top here is exactly the same quantity as in the, so numerator and denominator are the same, and here we only have d. And here we have those coefficients for beta and sigma I. So what we can do, now we can take all this quantity here, and we can introduce new variable I. And this is what happens here. So we introduce new variable, and we know that the initial will be changed because we also we handle this the scaling with respect to beta. So you can see that if we choose 0 here, this will nicely cancel it, and we will still have this beta factor here. So this is our initial, and we see also because we did only the constant change, so we added this the displacement. The dynamics of the processes are the same. So this means that dynamics for our Ji, this is the LIBOR under this displaced new LIBOR rate, it's given of this form. And then this Ji, it is, actually we have to only look at what is the initial value changed. Initial value has to be scaled according to B, beta. So, okay, so now what we have to do, so the first step was easy because we just removed this displacement. Some part of this beta is already in the volatility, and second part of beta is included in the initial value for our new process. Now, next step is to take those two constants and include them in the under the square root, and then we have to redefine our process for the variance. So you see it's a beta squared and sigma I squared. Now we take this quantity, the whole quantity, and we define new variance process, which is basically equal to that part. So then our new process for LIBORs, displaced LIBORs, is given just like we had for the Heston model. So there is no constants in front. Of course, now the consequence, we have to still find the dynamics for our V bar or new bar with these two adjustments. So this adjustment, which is here, that multiplication with respect to with beta squared and sigma I squared. And this is what we do here. So if we just apply ethos, it's very trivial because we have just a constant correction. But if you substitute the dynamics for new here for the variance process, we see that we have to adjust our volatility and also our mean reversion part. Actually, we can include this in the under the bracket because we would like to link the process to be in terms of V hat, right? So it's our new process. So this is why we multiply all these functions in the brackets. And then if what we do, we can actually realize that this is already of the form that we can represent our new process for V hat, which is basically here. So it's a dV hat is equal to V hat 0. And that is basically this part. Actually, this is this part. And then we have V hat on new hat. This is the definition of our process because we multiply with those constant. So of course, it's exactly what we had here, the definition. And then we have also this new correction or adjustment for the variance. So this will be handled with this here eta hat, and this will be represented here. Let me take a look here if everything is still fine, because it looks like, yes, so you see this beta squared, sigma squared. Of course, if we put under the square root, because here will be this new hat here, t, right? And then we also have to adjust our variance, the curvature part, so eta hat will be equal to this. So this is fine. So you see now we have arrived actually by the starting with displaced diffusion, stochastic volatility displaced diffusion, using some substitutions. Nicely, we arrived at the dynamics of the Heston model. And of course, in this case, still we have Heston model, but those two Brownian motions, so this is important, these are uncorrelated. So correlation equals to 0. However, some of the parameters have to be accordingly scaled. So there is some kind of relation between the parameters. If we have this kind of relations when a parameter of one process involves multiple different parameters, it's typically considered to be limitation of the model because there is some kind of correlation between the parameters. So if this kind of relations exist, so beta in both parameters, that's typically limiting to the model. So you can expect that displaced diffusion, even if you have stochastic volatility, it would be less flexible than if you compare it to the Heston model without reintroduction of this displacing coefficient. However, here we can still benefit from the fact that we have a model that allows us to smile, skew, and at the same time allows us to handle issues with the measures from the LIBOR market model. And that's very, very important because that was actually the main concern when we started using the Heston model in the context of the LIBOR market model. In this lecture, I have indicated that there are some techniques that we can use if we have problems with the dynamics of the LIBOR market model, especially if you would like to find some approximations. And one of the techniques which is actually the most common in the sense of the LIBOR market model, in application to the LIBOR market model, is the technique called freezing technique. Freezing technique is a very straightforward method which actually freezes the value, the stochasticity of the LIBOR. So you see, this is essentially the key point here, that approximation is that if we have LIBOR I at time t, we fix it at the initial value. And of course, you see that because LIBOR is a martingale, the expectation essentially would be also LIT0. So this is kind of, we can think of a projection on the first moment. However, this approximation destroys the dynamics and destroys the stochasticity of the LIBOR itself. So that's a big limitation. Of course, if we have a drift right now, you see this is the LIBOR market model under this spot measure that we have defined earlier. We have this complicated drift. And if we start freezing, so we see that there's actually, this should not equal sign, but should be approximation sign. So we see that if we start approximating, then this drift correction here that we have, actually everything here, this becomes constant. So then we are basically having very simplified case because now our drift that we had highly stochastic, depending on all the stochastic LIBORs defined in this framework, now suddenly everything becomes deterministic, actually in this case even constant, because depending on the sigma k function. So then from model to extremely difficult or highly advanced and sophisticated, everything just becomes rather trivial. And the question would be, of course, in what are the scenarios that we are allowed to use this kind of technique? And from my experience, I see that people often abuse this approach because whenever they see something which becomes difficult and rather sophisticated in the sense that they cannot really directly apply well-known techniques, always that there's an attempt to freeze values somewhere. Unfortunately, from the theoretical perspective, because of the high dimensions of the LIBOR market model, this is not really measurable in sense of quantification. You can't really quantify what error you're generating. The error that you will see will strongly depend on volatility term structures and also the yield curve itself. So if we have when it would work, it would only work in a sense that we have a flat volatility term structure. Then you can say, okay, there's not so much impact. So overall, remember, we started with the LIBOR market model that I introduced to be a tank that it can be destroying the problems or could be solving many issues related to pricing of exotics. However, if you abuse it and you introduce freezing, if you apply it too often, you may destroy the whole idea of using this advanced technique. Then your tank becomes essentially useless it is still a big piece of metal that you have to deal with. However, you cannot really solve it. You cannot solve it the problems that you started with. If you abuse your model and you really start enforcing some kind of a brute force approximations, like for example the freezing technique, then I would say maybe in some scenarios you should not use LIBOR market model in the first place. Maybe you should stick to short rate model in which you would not introduce any kind of approximations like this. So I would say overall you can use it, the freezing techniques, because this is the technique which is commonly applied. However, you have to be very careful and really check what the error you're generating, depending on the market scenarios, whether the volatility it is, what is the term structure of volatilities, where are the yield curves, what are the level of interest rates, and especially what is the structure of your payoff. Of course, if you are calibrating your model, freezing technique can be handy because it allows you for some kind of, let's say, guess estimator for your parameters. However, you should not rely on those parameters as the reliable ones if you have used approximation which really destroyed the essence of the model you are interested in. So enforcing the LIBOR freezing may significantly limit the purpose of the LIBOR market model, especially if we have stochastic volatilities. So be careful, always think twice, and if you do freezing, always make the comparisons of the values of your derivative. What is the cost of the freezing? And then if you know your error, you're able to estimate the error you generate, maybe you can incorporate this error in somehow in the management of the risks you have, because that essentially is a risk that maybe at some point cause some significant financial losses. So always be careful if you do freezing, do it only if it's necessary. As a financial engineer, you will often hear the term convexity and convexity correction. In this block, I will explain what is the problem with the convexity correction and what tools we have in order to address this issue. The term convexity correction or convexity is very often used in finance, and this concept of the convexity adjustment is always required and for all the asset classes, so this is nothing particular to interest rates, and this takes place when there are, this is very important, when there are payment delays or when the moments of the payment do not correspond to the payment date of the numeraire. This is maybe sounds a little bit complicated what that means and what are the scenarios where we have a payment of our contract would not correspond to the numeraire. This will be very clear in coming slides. Essentially, if we look at the very simplistic case, so this is the case we have seen already before in this lecture, we have a LIBOR rate, and LIBOR rate has a natural date Ti, so this is the payment date of the LIBOR. And of course, if we have a payment taking place at time Ti, we can discount this amount to time T0. So if we change measure from a risk-neutral measure Q to the numeraire corresponding to the zero coupon bond, so this will be the forward TI measure, then this is the expression we have for this relation. And of course, now we see, okay, this LIBOR, it is martingale under TI forward measure. So this is what we have seen before. So this means this will be equal to the LIBOR at time T0. So this is very nice. However, the problem is that if we have a contract, which is here in the denominator, but it's not, payment doesn't take place at time Ti, but for example, at time Ti minus 1 or time Ti plus 2, then we have a misalignment between numeraire and the asset itself, the observable asset we would like to price. And then this can cause problems. Of course, the question would be when you see these problems. And of course, those problems will be not present if, for example, you have full white model and you have simulated LIBOR dynamics, you have also simulated money savings account, and obviously, but it doesn't really matter what date the payment will take place because you will simply substitute the simulated Monte Carlo paths and you will just evaluate the expectation. So then we don't really talk about the convexity because essentially your model, you are just evaluating expectation, expression for your payoff. So if you have a stochastic model and you substitute the quantities that you have simulated to this expectation, then you don't really see the convexity issue. Of course, the problem is when we have this kind of relations, that we are like to benefit that this would be equal to the LIBOR today. So you see that if we have this asset, we would like to price it. In essence, we don't need any stochastic model to evaluate this expectation because we use these properties of martingales, and we know that this whole term basically would be purely driven by yield curve. However, if we don't have this alignment between payments, then we cannot really rely on a yield curve because this instrument is not the instrument that was used to build yield curve. So here we have a forward rate, and this is observable in the market, and from that we have implied the yield curve. So then we can always move back, we can always get this expectation back from the yield curve. However, market doesn't give us different type of derivatives. Those need to be calculated using the stochastic models. So if market gives you prices, for example, for forward swaps, you can reuse those quantities, so you can reuse those expectations to price your derivative. However, if you have a contract which is slightly different, that is what is available in the market, this means you have to somehow estimate that expectation. And that's related very often to the convexity, especially if the payments do not agree. So let's take a look at in this case, what we have seen in the previous slide, this will be equal to the zero coupon bond times the LIBOR rate. So okay, in this case here, we can purely evaluate by looking at the LIBOR rate estimated from the yield curve and also zero coupon bond. So then we know explicitly the price is given in terms of yield curve. We can just get those quantities from yield curve. However, if we have something slightly different, if the payoff is slightly different than what we see in the market, then we cannot make this usage of a yield curve. And this is example here. So here we have a LIBOR, exactly the same as what we have seen before. However, now, for example, you have a client that he would like to get payment. So the cash flow should take place at time ti minus 1. So this LIBOR rate we have here, this will be time today. We have a time ti minus 1 time ti. In a standard approach, so this was in this case here, we had exactly the same. And then we had a payment that took place at this date. And then, so this means we had to discount to today. However, in this contract, the client would like to have payment at this date. So we have to discount this amount here. And this is slightly different what we have seen in that previous contract. So these two are two different quantities. Okay, so let's take a look how we can solve it, whether we can actually still the solution for this expectation we can express. So this expectation can be expressed in terms of observables in the market, in terms, for example, of zero coupon bonds that we can see or we can generate using yield curve. So what we do first, we will switch the measure from the risk neutral to the numeraire to zero coupon bond to the forward measure ti minus 1. So again, we apply the measure change technique from the Radom-Nikodym, and this is the transformation we have. So we switch from risk neutral to ti minus 1. And then if we have this Radom-Nikodym derivative, we can substitute in this expectation. So we take this term, we substitute it under this expectation, and this is our valuation expression. So nicely, this money savings account will cancel out with this term. This will cancel out with this one. So this is actually 1 anyway. This zero coupon bond can go outside the expectation. And then we are only left with this LIBOR and this zero coupon bond here. Actually, this zero coupon bond is even equal to 1. So that's also nice. So if we go further, this is what we arrive at. We arrive at the expression for our contract is notional times zero coupon bond. So this is immediately we see it's easy because we can calculate it using yield curve. However, now the remaining part is expectation under ti minus 1 measure of this LIBOR. But this is not anymore something we have seen before because we know that LIBOR is a martingale under ti measure, but it's not martingale under ti minus 1. So this, you cannot simply say this will be just the LIBOR rate at t0. So this is exactly what the problem, how this convexity adjustment, how this convexity correction would kick in. If, for example, you would have instruments in the market that you can imply this, that's perfect. However, in what we have seen so far in this course, This is not the standard product that you would see in the market. Market gives you market instruments, swaps, etc. Those are presented in their natural measures. And this is the this is the bottom line here. So we have this these two expectations, and we have a ti minus 1 measure. We have ti measure. Those are not the same. So this library is not the same. However, the expression on the right-hand side, because it's a martingale under ti forward measure, then we know this. Of course, you could say, okay, this will be the approximation. We can still have a notional times 0 bond t0 ti minus 1, and then we multiply with this L t0 ti minus 1 ti. So of course, this would be the kind of, you would say, okay, let's just approximate. And of course, that's what you can do. But the difference between the real value of this expectation and your approximation, it is equal to the convexity correction. So in order to make this equal, you have to do something more, and that's the element that you add in order to have equality. That's called convexity correction. And this is actually the whole idea of this block, to explain you how to deal with those terms when you have expectations under different measures than taking that the pay dates take place. Then you have to do something extra. So let's go back. What we can also try to do, we can switch measure. So we have this expression. We have this expression of this term. We can also try to switch not to the ti minus 1, but we can switch to the ti measure corresponding to the payment date of this LIBOR. And then we will see, okay, then we know that LIBOR will be martingale under ti measure. So that's another attempt. Let's do that too. So this is the term that we will have for the Radon-Nikodym derivative. So we switch from ti minus 1 to ti measure. That would correspond to this payment date. So we want to switch from this ti minus 1 to time ti. And this is the expression we will have. So we start, of course, with what we have seen in the previous slide, expectation under ti minus 1 measure. Then we have a substitution of these ratios. Of course, some terms will be, of course, this will be canceling with this term. We have this term would go outside of the expectation. And this term will equal to 1. It's equal to 1 because it's just a zero coupon bond. And then we only end up with a ratio of these two bonds. Yeah? So we can take this one actually outside. But this, you see, here we have a quite interesting combination, because now this is constant, so this can go outside. Now we have a LIBOR, which is a martingale under ti forward measure, so this is perfect. However, this quantity, this is not any martingale. You see, the product of the two, it's a problematic issue, because we know that the LIBOR itself is a martingale. However, we don't know whether LIBOR divided by this zero coupon bond is a martingale. It's actually not. So this means that we have a problem, because still we cannot use the properties that we would like to use, that LIBOR under ti forward measure is a martingale. However, what we will do next, we will try to reformulate this problem of this convexity in such a way that you will have a forward. So our expression will be in this way. We will have expression for our trade equal to this term plus some convexity correction called CC. And we try to determine what is the CC such that we will have no approximation here, but it will be equality. So this will be the basic idea. So first, estimate, let's say, approximation based on this naiveness of saying, okay, this measure doesn't really matter, it will be just ti. And then we will try to determine what is the correction term, the convexity correction that we have to add to this term, such that this error that we did because of the approximation is reduced, or actually it's removed. That will be the idea. And what we can do the following. We can just add and subtract LIBOR. So you see this expression here is exactly equal to here, except now we have this nice combination. We have first expectation of the LIBOR ti under ti forward measure, and we have this additional term. And of course, you will see this multiplies with minus 1. It will cancel with that term. But at the end, this is just a nice representation that we can say, okay, this term, the first part, corresponds as a martingale, so everything is good. And this part is this convexity correction that we would like to derive. And then we have to do some modeling choices how to derive this convexity correction. So the first part, so this is exactly what I'm doing here. So the first part, we have this LIBOR rate. So here, we know it's a martingale. And then from the other side, we have a convexity correction term. So of course, now the objective is, okay, we found some kind of, let's say, expectation term. And now we would like to find out what is the adjustment we need to take into account to have this equal sign in this expression for the variance, for the trade value at time t0. Like I said before, keep in mind that this problem will not exist if you have a model that is simulated with Monte Carlo. Then you can just substitute your paths in expression for LIBOR rates and also for money savings account. This problem will not exist there. However, we would like to avoid as much as possible simulations, especially if they are not needed, because if you have a, you can of course, if you have a swap, you can also evaluate swap using Monte Carlo simulation, but there is no real need for that because you can imply the value of a swap from yield curve. So this is the strategy we want to have here. We have to calculate a trade, a value, using the simplest possible blocks. And of course, the block which is the most important is the yield curve. And then the adjustments we do according to some other market instruments. So let's see here. So we have this expectation, this convexity correction. We have this product of these two terms here. And of course, this multiplied by -1, then we get this LIBOR out. And only one part we have to focus right now is this expectation under TI forward measure. And then we have this ratio of LIBOR and zero coupon bond. And of course, this is not, we cannot say this is a martingale because you see, this LIBOR is a martingale under TI forward measure, but the whole quantity LIBOR divided by zero coupon bond is not anymore a martingale. This is a problematic here because if we just write the definition of a LIBOR rate, you will see that you will have some squares regarding zero coupon bonds. So that's not really tradable assets because we have squares. So that's a big issue. But what we can do, we can write this zero coupon bond using definition of the LIBOR rate. So this will be this is the definition. So LIBOR, of course, LIBOR consists of this zero coupon bond. So we can rewrite the zero coupon bond in terms of LIBORs, and this is here. And then we can substitute into this expectation. So you see PTI minus 1 TI. We can substitute this term into this expression here. Of course, here it will be the product of LIBOR. So this is what we will see. So then if we substitute, then we end up with a very nice, very interesting expression. The first part is LIBOR at time t0. So this is fine. And then we have this, so this is deterministic, everything is nice. And this comes from the fact that we have this this part here. Actually, so if we substitute this zero coupon bond and this term for that, you will see that we multiply LIBOR with 1, and that 1 is basically this expectation will be martingale under T forward measure. So we don't really look at this term yet. This will be later. But now we're only looking at this expectation. So substitute, and you will see that what will come out is this LIBOR I at time t0. And then we have this expectation on the TI forward measure. And then what we have here is a LIBOR squared. So obviously, this is also something we have already discussed previously in this course. LIBOR squared is not a martingale under TI forward measure. And the problem, of course, to see that, you can do the following. You can define the LIBOR dynamics. This is, let's say, log normal LIBOR rate. If you apply Ito's lemma, you will see that we have a drift term. This means that this cannot be a martingale under that TI forward measure. So, however, what we can do, we see that at the end, in order to get this value valuation of our trade, we need to find this expectation TI under TI forward measure. So of course, now what we can do, we can assume that we have this dynamics for the LIBOR, and we can just evaluate this LIBOR solution. We can substitute to this expectation, right? So we know the solution for this expression. We are basically squared of that solution for L, and then we take the next step would be take the expectation. And of course, this model is very simplified because we can just take the expectation, and this expectation will be analytical, and this is what we will do here. So if we start with assumption that we have some stochastic LIBOR market model, of course, our expectation depends only on one single LIBOR, so that's not really complicated. We can just start with the dynamics for that particular LIBOR. We know the solution, that LIBOR because it's geometric Brownian motion. So the solution is of very simplistic form. And then what we do, we substitute this LIBOR into the expectation, so for this LIBOR square. And of course, squaring of log normal random variable is very simple because everything will be squared. So, or everything in exponent will be multiplied by 2. So if initial will be squared, then we have a 2 times minus half sigma squared ti minus 1. So this will be basically sigma squared ti minus 1. And then we end up only with the expectation of the exponent of Brownian motion. And this expectation, of course, it's closed form because it's just a Brownian motion here. And the whole expression is equal to this term. So this means that if we collect all the terms we have derived into the one term for the convexity correction, everything is nicely given in closed form. So the convexity correction will consist of terms that we can see from yield curve. So this will be from yield curve, this will be from yield curve, this will be from yield curve, and these two. Only one part which is still to be established is the sigma, because now we found in order to get this expectation, we define some LIBOR rate, the dynamics for LIBOR rate. And this LIBOR dynamics depends on sigma, because everything, so the LIBOR initial, so L times T0 is null, because we know this from the yield curve. Only one unknown is sigma. And of course, this is the quite problematic issue, because which LIBOR, which volatility, even if you have an implied volatility smile skew, to which volatility, so if we have a, take a look here, I will have strikes K here, we have implied volatility here in percentage, we have some maybe implied volatility smile skew, so this will be, let's say, at the money, ATM. And of course, depending whether we go left to left or to the right, we may have different strikes, and of course, we will have different volatility levels. So which sigma to choose such that this expression will be correct. And of course, if we look at this expression, this expectation, it's very unclear what is the volatility or what trade can we think of, what is the corresponding strike from this picture. So this is still a problematic issue. How to choose sigma so that this expectation will be properly calculated. Of course, the obvious choice or the simplest would be let's take just at the money, because we don't know anything more. We don't have any additional information. Then we take only at the money volatility. But of course, we forget about the whole impact of the volatility smile. So we have only the at the money level. Of course, that would be a very natural choice, but I will show you later that there are better methods on how to choose sigma. And actually, it's also possible to take whole sigma into account, so whole volatility smile into account in order to evaluate this expectation. We don't need to make a particular choice whether we are taking volatility from this point or at the money on some other point. We can actually take whole information regarding smile or skew in the market in order to calculate this expectation. And now I have also prepared an experiment, so the Python experiment, where we evaluate. So the blue line is the experiment with the convexity correction. Blue line represents the value of derivative. Of course, value of derivative does not depend on sigma, because this expectation is known, is calculated, let's say, given from the market. And of course, now we have this approximation relying on the dynamics of the LIBOR market, LIBOR dynamics log normal distribution. Then you see that depending on sigma, we may have different values for the convexity. So this is the value of derivative, this is the value of convexity. So you see, if we change sigma, sigma goes large, then this convexity adjustment will be higher. If sigma is decreasing, then it's smaller. So you see, in this case, actually, we know that the best sigma to actually match the market would be sigma around 0.22. However, how would you know that a priori? So then for that, you would need to either generate, let's say, Monte Carlo simulation to actually not to deal with the convexity correction, or if there are market instruments that indicate what is the expectation of this contract. So for example, if we have a market expectation, so if market gives you this price, for example, somebody tells you what is the price of this derivative, but essentially you are able to back up what is the sigma for this convexity correction. So this is something how financial engineers would look like. we have a model. We have a model for this expectation. We know that there is some kind of unknown parameter sigma. We don't know where to specify it. We have some freedom how to choose it. Then what we'll be looking at the market instruments that allow us to calibrate the sigma, how to extract the sigma from market quotes. Of course, the one possibility would be to approach it, like I just said, if there is this expectation or that trade is available in the market, we can do some kind of Newton-Raphson algorithm to find out what is sigma that basically we are pricing back the market values. And this is let's say financial engineering approach to handle this problem. Now let's take a look at the Python implementation. So it's a very simple implementation. Here I'm using this is the White model for generation of the paths. I have specified two dates. So we have this LIBOR with 4 years and 8 years. So it's a period between 4 and 8 years. Here I'm calculating zero coupon bond. We have also LIBOR between that period. And here you see, in this case, I'm calculating expectation and for 1 over, so we have discounting of that LIBOR. And of course, keep in mind that in a White model, if we have a LIBOR rate from time t1 until time t2, we only need zero coupon bonds at time t1. So you can see that generation of Monte Carlo paths take place only until time t1, because then we benefit from this affine representation, this exponent a plus b times rt. And then this means that we can actually calculate at this point t1 all the bonds from starting from time t1 to any point in the future. Of course, the yield curve needs to be taken into account. So then we discount this amount. So this will be our reference value. And then we have a second part where we calculate this convexity correction, so CC. And then this is expression that we have just derived. And this expression depends on parameter sigma that we have to choose. So this is very simple simulation where we can just replicate the results from the previous from the slides. I also on the top I here always, like I already mentioned before, always if I have Monte Carlo simulation for any short rate model or any model, I always first try to check what is the match between yield curve from the market, our input, and what is the yield curve implied from our model simulation. Then we can actually have confidence that Monte Carlo simulated paths are fine. And here's also some statistics. What is the convexity correction that has to be taken into account? And this is the impact. So we see again 0.22, that will be the ideal sigma, such that we can recover the price given in the market. And this will be basically that will be it. What is important to keep in mind that often when you deal with convexity corrections, you always have to play with those measure changes. So already in lecture 2, we spent some time discussing possibilities, how to choose measures. And here in the convexity world, when you talk about the convexity corrections, you have to be very fluent with the measure changes to really extract, to really see this impact of the volatility. So this is a little bit of art, but in time, once you do not your first convexity correction, but maybe the 8th or 10th or 100th, then you will get much more confident and you have much natural feeling what is available in the market, what are the reasonable model assumptions you have to do, because also in this case, the LIBOR case, we have to specify some dynamics. Yeah, so we also had to make some choices before actually we can actually imply this volatility parameter sigma. Now, I would like to add a few words regarding the alternative approach, where we don't need to specify particular sigma, but we can take whole smile and whole implied volatility smile and skew into account in order to evaluate that expectation. As already mentioned, it is difficult to choose optimal sigma. We can do it, of course, if we have available market quotes for this derivative of interest, then this volatility parameter sigma can be implied. But of course, it's easier that we can have let's say, implied volatility smile and skew, and we take immediately the whole smile and skew into account in the valuation of expectation. Then we don't need to rely on existence of some derivatives. So one possibility again is that you imply this parameter from the market. However, if you don't have market data, there's no available trade in the market, then you have to take everything what you have in available. And of course, This means that evaluation of this trade is also important to keep in mind. That doesn't rely only on the yield curve that we used to have, but also relies on implied volatility surface. So this you see that the complexity from linear product become non-linear. So this is also the convexity part, because it's non-linear product essentially that we have to price. The approach that I would like to mention it, details on this technique, it's out of the scope of this course. I will discuss it in detail in the follow-up course, but I would like to still to mention so that you know that you'll be aware of existence of such a technique. The technique I would like to mention here is called Braden-Litzenberger approach. So Braden-Litzenberger, essentially, they found out, this was a very old article from the 70s, that if we have some expectation of any variable, for example, here we have an expectation of a LIBOR, then we can actually express it in terms of the, let's say, in the money value. So this is the initial, you see, it's the same term as we had here, the expectation evaluated at time t0. So this is nice because it's essentially what we would like to have. And then we have this correction term. And correction term involves integration of calls and puts of implied volatility smile based on the implied volatility smile. So you see that actually here, this is definition of a value of a put. So it's a floorlet for the interest rates on interest rate. Underlying is the LIBOR rate, and here is the part for the strike K. So you see, in order to get this correction, we have to evaluate this integral over from 0 until the on the money level, and we calculate integrate put values. And on the other side, we have extra other term that we integrate from in the money level to the infinity, and with that, then we take calls. So this is also K here. So you see, in this way, if we have this implied volatility smile, so this will be our at the money level. So this would be, let's say, like this kind of shape. Then we could take the sigma as the naively at the money. However, here in this approach, in the Braden-Litzenberger approach, we can take basically the expectation frozen at time t0, evaluate at time t0, and then we have this integral over this period until time at the money, because the strike goes in this, we're integrating not in the time direction, but strike dimension. So we integrate the first part, and then the second term is integration from at the money level until the infinity. Of course, this infinity part doesn't really matter because options will become worthless if we get to this large structure. There's a limited point. This technique is very powerful because it allows us to calculate all sorts of expectations. So this is applicable for European type of options when our payoff depends only on one instant, one payment. So this is exactly what we had in this expectation calculation, because there we had one payment that took place at time ti minus 1. And then we can incorporate the smile impact to smile effect into this evaluation. And of course, in this approach, we don't need to rely on the market availability of sigma, of any product that we can imply our sigma. We simply take implied volatility smile and we just evaluate at all the strikes, calls and puts, and then we get this convexity correction term based on the Braden-Litzenberger approach. Of course, in this case, everything relies on available implied volatility surface. If you don't have that available, then it's not really going to help you. Then maybe assuming some log normal distribution or other type of distribution for the LIBOR dynamics is maybe more efficient, more straightforward than building a whole volatility surface to get this particular quote. Details again on this Braden-Litzenberger and derivations, how to get to this a very much elegant expression for pricing of for this, let's say, these complicated expressions depending on marginal values of calls and puts. It will be covered in a follow-up course, but keep that in mind that such a possibility exists. Now is the time to summarize today's lecture. In today's lecture, we have discussed two main subjects. The first one was the LIBOR market model and possible extensions with stochastic volatility. And the second subject was the subject of convexity corrections, where we encounter where there's a misalignment between assets that we have we observe and also the discounting factor. So if this is misaligned, the numeraire and the asset, then we often have to deal with the convexity adjustments, and that for that impact, for that evaluation, we need some model assumptions and actually model to be evaluated. So let's take a look what we have done today. We started with a little bit of history about the LIBOR market model, to GBM, BGM, sorry, Brace Gontarek Grzelak model, and then we specified what are the model assumptions of the LIBOR market model. Like we discussed also earlier, that the contribution of the authors of the model was to linkage between different LIBORs defined under different measures, and taking them together and define one uniform measure can be used to evaluate derivatives that depend on multiple LIBORs. Because like we have already discussed many times in this course, if we have a trade, we always have to make sure that underlying processes have the same measure as the expectation. So if we have expectation, let's say some measure A, and this we have some payoff here, we always have to make sure that the processes used in this evaluation of this payoff always have Brownian motion under A measure. So it's to be one process I, we have a process DW2. Right? So every process which is used in evaluating this expectation has to be under that measure. So the LIBOR market model brings all those processes under one unified frame. And then this was the subject of the next point, where we described the discussion. We started with the dynamics for the LIBOR under the P measure, and then we switched to the T forward measure. Another 2 points here was the measure changes, how the measure evaluation, how those LIBOR dynamics would change if we change measures. So because we have multiple LIBORs, and what is the dynamics, how those LIBORs will be affected by this measure transformation. And that was shown that if we have those LIBOR rates, those will be including extra term summation term in the drift in order to compensate for the measure changes. So the measure change will be in the drift, and drift sometimes becomes very complicated. Another subject discussed was the terminal and spot measures. So those, I showed you what are the differences between the two measures. And of course, we spent most of time regarding the spot measure and the creation of the so-called money savings account in the discrete tenor structure of the LIBOR market model. Then we had two subjects of the stochastic volatility. We have discussed what are the naive way of approaching this problem and adding correlated volatility to the LIBOR dynamics, so kind of resembling Heston type of approach, and what kind of problems that would have if we start changing measures. And the second part, where we have solved the problem of the very complicated volatility structure, and by changing model from Heston to displaced diffusion, and then assuming some zero correlation between the variance and the LIBOR rate, and by introduction of displaced diffusion coefficient, we could somehow compensate for the lack of correlation by displacing the volatility coefficient. So that was the important takeaway. Here I also mentioned the freezing technique, so the popular technique in approximating of the LIBOR market model, and what are the pitfalls, problems you may encounter. In the rest of the lecture, I have focused on convexity corrections and how to think about convexity correction when we see the convexity issue, and how to handle it using some model assumptions. And what is the problem, and how to solve this problem, and how to specify a model dynamics that we can evaluate those additional nonlinear expectations that we have to handle if we have convexity that is not properly calculated, or is actually missing convexity, how this leads to those involved expectations, and then how to solve those expectations using stochastic differential equations. And now it's time to summarize the summary and the homework. So the summary we have done. For today, I have prepared 3 assignments. The first assignment is about the relation. So we have a compounding LIBOR rate, and you have to find out that this equality would hold. So this is a little bit of algebraic exercise where you have to substitute the definition of the LIBOR rate and show that this equality for so-called overnight index swap, that will hold. This is assignment number 1. Assignment number 2 is something that we haven't discussed in this course, but I think you will find it very interesting. So this is a model where we have an extension of the Heston model. So we don't have one variance process, but we have two variance processes. Those variance processes have correlation zero, so everything is independent. But essentially, instead of having one volatility driver, we have two volatility drivers. And those are the volatility variance processes, CIR variance processes. This model is called double Heston model. So you can look it up online. What are the advantages, disadvantages of the model? And your assignment is to represent this model in the following form. So you have to do some kind of maybe compression of the factorization of the Brownian motions such that you can arrive at this expression. So you have to find out what is psi bar and what are the initial values for these two processes. And the third assignment is the convexity correction calculation. So in slide number 43, we have discussed convexity adjustment using this dynamics for the LIBOR rate. Your assignment is to do something very similar, however, also slightly different. You have to do the same calculation. However, in this case, you have to look at the displacement, so we call shift parameter that is introduced to handle, let's say, negative rates that could be available or are present in the market. So this is the assignment. Those are three assignments. I hope you enjoyed this lecture and we see each other next time. Bye-bye.